Hello. This is the first episode in a series on set theory, which is a form of mathematics that tries to get to the or tries to provide a logical foundation to mathematics. Within the series, I will be we will be listening to Logos, who has a master's in mathematics, and we'll be going through Charles C. Pinter's book, A Book of Set Theory, which is an excellent textbook. I recommend that everyone listening gets it to follow along. And basically, we'll be going through the fundamentals of set theory and then expanding upon how they are related to various philosophical topics. So, all right, Logos, if you'd like to just give us a introduction to set theory and sort of give us a forecast of what we'll be talking about through at least this first episode here.
Sure. So the main reason we're talking about set theory, I think, is because of how much it's implicitly or explicitly in tons of arguments about philosophy, which is something I know you like to cover on your channel. So it's explicitly in arguments like, say, the Kalam. There are no, like, the past can't be infinite because hand waves at Hilbert's Hotel, or things like that. But it also implicitly shows up in arguments too. So God can't be omniscient. Why not? Well, suppose there's a set of all truths, and games are played with power sets, which sounds kind of crazy, and we'll talk about those later. But the nuts and bolts of set theory are in a lot of these arguments in very interesting ways, and it's hard for people to get a grasp on it because a lot of people who go into mathematics for mathematics' sake don't often become, major philosophers that write about this stuff, and the people who write about philosophy don't often engage real deep with the mathematics. So getting a bridge between them could be very, very difficult. I like Chapter 0 of this book a lot more than I remembered when I initially read this book. I was reading a couple days ago, reviewing for this, and there are several things that I liked that he talked about. So the first thing that he mentions explicitly is the existence of actual versus potential infinites. And you might recognize that if you're in the philosophy of religion space, because that comes up all the time when talking about the Kalam. And after grappling with it for several years, asking what these people mean by this distinction, the most clear answer to the question I've actually saw in this book, and he wasn't even meaning that argument addressed to this audience. And so it's just kind of crazy to me that there it was. The next interesting part we can look over in Chapter 0 is the paradoxes of set theory, because so much of the implicit arguments about God, say omniscience and things like that, often depend on these paradoxes and what we're including as sets. Josh Rasmussen regularly likes to talk about this stuff. There are self-reference paradoxes all over the place that are very Russellian in nature. And so you can talk about God's omniscience, you can talk about his omnipotence, can God make a stone too heavy for him to lift? You can completely restate that argument purely in Russell's paradox-like terms. And so these paradoxes and how they're structured and stuff become the underpinning for all sorts of these arguments. And the next thing I think that's interesting. Yep.
So just to provide a bit of understanding for our audience, what is the advantage to stating paradoxes or other philosophical concepts in set theory terminology?
The advantage is if you can successfully do it, you can kind of take on a whole wide variety of paradoxes all at once. And if you don't really understand the structure of how a paradox is constructed, they can kind of be whack-a-mole. And it's like, okay, I think I found a solution for this paradox. And then some other cousin to it pops up and you're like, darn it, I wasn't expecting something like that. Let's find another solution. And this is what Alexander Proust in his book Infinity, Causality, and Paradox describes as, trying to find a cascade of ad hoc solutions, basically, where you solve these paradoxes one at a time until you have this giant binder full of ifs, buts, and provisos for dealing with all these paradoxes. Whereas if you can find something that links them all together, and they're all special cases of this one general thing being violated over and over and over again, well, if you can solve the the body spawning the Hydra heads. You cut off all the heads at once, to put it, very brutally.
All right, excellent. So then I think we should probably introduce Russell's paradox, as it is the most famous of these paradoxes and the most relevant, perhaps, to the development of set theory. So if you'd like to take that away.
Yeah, so before we get into the set theory version of it, we can just start with the kind of layman's version of it, the conceptual version of it. Suppose there's a barber shop in a town, and on the sign of this barber shop, it reads, this barber will shave the head of any and only person who does not shave themselves. And so Russell's question is, well, who shaves the barber? So if the barber shaves himself, he's violating his rule, because he's only supposed to shave the head of people who don't shave themselves, and, well, he'd be shaving himself. But let's suppose he does not shave himself. Well, he's supposed to shave the head of anyone who doesn't shave himself, which would include him, and so he's supposed to shave himself. So what do you do with that? That's basically the paradox in a nutshell. And before we get into like the set theoretic solutions and the expression of it, let's think about how you would solve it conceptually and how that would map over to all the set theory solutions. One way you could solve it is just by thinking about town, whether the barber is a member of a town, right? So the barber will shave the head of anyone in town, any and only those in town who don't shave themselves. So one trick is, well, does the barber live in town, right? Maybe the barber lives outside of town, and so this paradox just doesn't apply to him. Clever barber. Another trick would be to say, should we even assume in the barber making this sign that he does shave himself? Maybe no self-respecting barber would ever shave himself, because he could never do his own hair justice. So implicit in something like that, it just doesn't make sense for someone like a barber to shave himself. So we can put that assumption off the side. Or maybe the statement, the barber shaves the head of anyone who doesn't shave themselves, itself is a silly statement, because it could include the barber, and what do you do with that? And so those are like three different kinds of solutions that you might see. The most intuitive to me is maybe the barber doesn't live in the town, because there's less semantic play there, I think, than with the other ones. But now that we've kind of got the concept of what's going on here off the side, this is a cannot but must paradox, basically. There's one rule saying you cannot do something, another rule saying, yeah, but you must do something in case you can't do it, right? So you end up in a circle where you can't but must over and over and over again. And so trying to break that cycle is basically the way the game is being played. Now, let's try to state this, visualizing what's going on in your head with sets. We're going to define a set, call it S. So S is supposed to contain every set that doesn't contain itself as a member, right? So it's a set of all elements it's a set of all sets who aren't elements of themselves. So it contains only things that aren't elements of themselves, because you've explicitly bounded S, and it contains anything that's not an element of itself. And this is why the barber analogy works. In the same way the barber shaves the head of any who don't shave themselves, S contains all the sets that aren't members or elements of themselves. And just like you asked, does the barber shave himself? You ask, well, is this big set S an element of itself or not? Well, if S is an element of itself, it can't be, because all the elements in S are things that don't contain themselves, and we just said S does. So, oops, that's bad. Okay. So S does not contain itself as a member. But if S does not contain itself as a member, remember, S is supposed to contain everything that doesn't contain itself as a member. So S should contain itself. So either way, no matter which direction you go, you run into a contradiction. Just like if the barber doesn't shave himself, then he should, and if he should, then he shouldn't. Same rule. It's a can't but must paradox. Now, just like the way we solve it with the barber, we could solve it several ways with set theory, and here's where the chapter is going to kind of go, and I'll kind of forecast it a little bit. In the same way, we could ask something like, well, maybe the barber doesn't live in town. There are two ways you could solve it. You could say that maybe this thing S, that contains things that aren't elements of themselves, that's not a set. In the same way that barber doesn't live in the town of the people he shaves, this big class of stuff isn't a set. It's a class, and we'll talk about that later, right? So classes are these big things that talk about sets that aren't sets, and so they can't be roped into these circular paradoxes, right? Another trick you could do would be like Russell's type theory, where you instead of defining this thing that's set versus class as like this big distinction, you could have types. Russell has this theory of types where you have types of orders, and this is described in this chapter of the book. I never studied this, so I'll go off what this says. And there's all sorts of vernacular to describe like how big the types are, how to describe them semantically, and it's very complicated. Although interestingly enough, apparently computer scientists love how complicated it is, how explicit it is, because it's very, very, very easy to write into a programming language, whereas other set theories are very intuitive. So mathematicians hate it because the rules are so convoluted to like write intuitive proofs for, but like programmers love it. So it's seemed like a resurgence apparently. So it's, I don't know. Anyway, but in the same way you could say that the barber doesn't physically live in town, you could have types, right? So the barber lives in a county, maybe not a town. So it's a different type of thing. You could also say that just semantically, if you include the barber, you can't be talking about all the townsfolk because it wouldn't make sense. That's like the set versus category distinction. The other way you could solve it is you could say that certain statements just don't make sense to say. Like, take all the things that don't contain themselves as members, right? Under ZFC set theory, Zermelo, Frankel, Cantor set theory, that is not a proper description of a set, because in order to do that, you have to be specific. I want every element in something bigger such that thing is true. Without the bounding thing, in general, we call this a universe of discourse, right? If you're going to be specific with a set, if you're going to use like an axiom of specification or something to be specific and describe things in a set, you want to pull them from some bounded universe of discourse to make sure you're not making stuff too big. So I've said a lot. Let me put a little pause there for a second and take the opportunity to distinguish between two types of set theory that we'll see: ZFC versus what this book is going to cover. And this is a big forecasting that the author goes over. So ZFC is very, very much in the vein of axiom of specification, where, in order to specify what's in a set, instead of just describing something vaguely like let X be a set, you want to pull from this universe of discourse. You want to pull from specific things to bound things, to make things small and manageable. This is von Neumann set theory, which is covered in this book, which has a lot of similarities, but the big difference is we intuitively don't think about sets in this very, very bounded, small way. We want to talk about a set of all. That picture you got in the top left right there. X is an element of A such that S of X. This is basically like the ZFC way of solving the paradox, or at least one of them. So this is how ZFC solves the problem. How von Neumann set theory will solve the problem is the set versus class distinction. So what it will do is it will say, look, we can talk about these unrestricted things all the time. Let X such that blah, blah, blah. I don't know what big set they come from. Consider the set of all people like Socrates. What's the big set? Is it all people? Is it all people in Greece? Is it all people on planet Earth? Is it all possible aliens? I don't know. I don't care. I shouldn't have to answer that question, right? I like to have unrestricted things and talk about properties of them, and it shouldn't be a big deal. And so the way that this kind of set theory gets out of paradoxes is it just says, look, if it looks like the things you're talking about are so big, you can introduce paradoxes on them, then really what we're going to say is, oh, that's a class, not a set. So how would both of these things, not from the intuition of like the barber, but in set theory, solve the problem? So imagine we try again. Instead of saying, let's do ZFC first. Instead of saying, let S be a set of any sets that don't contain themselves as members, you'd have to say something like, well, let S be any set in a universe of discourse that doesn't contain itself as a member. Well, does S contain itself as a member? If it does, then it can't. Okay, that doesn't change. But let's suppose S is not an element of itself. Well, then it should be if it's unrestricted. But what you can always say now that you're in ZFC land is, well, S is just not going to be in our universe of discourse. So S isn't an element of itself because we've restricted the stuff we can pull our sets from to make S, such that S isn't in that stuff you can pull from. So it's not a member of itself, but not in a way in which it should be, because we're only talking about things in you or in whatever you want, your universe of discourse, that don't contain themselves. So even if S isn't in there, maybe it's not in you, who cares? I don't know if that makes a lot of sense verbally. Maybe if you rewind it and listen a couple times, you'll get it. But it's hard to kind of say it out because it's it's a lot of words and terminology and letters, and you just kind of vomit it out. Drawing it out isn't much better. You see a lot of statements like on the bottom right of this page here, and mathematicians just kind of like and just vomit it on the page, and people kind of have to follow it and get headaches and think about it for quite a while. But hopefully it ends up making some sense. Those are the two big solutions: the ZFC and like let me describe the set versus class distinction. It's very similar, right? Just as before, what if S doesn't contain itself? Well, plausibly, S is a class, not a set. So if S contains sets that don't contain themselves as members, and it turns out that S is a class, well, a class doesn't have to be an element of if it, sorry, let me say this carefully. If it contains sets that don't contain themselves as members, but it's a class, and class is different than set, then it doesn't have to be in itself, just in case it doesn't contain itself, because it's not a set. So it's kind of semantic trickery here, but it kind of dodges the paradox. And how it does so is it just says, look, if it's getting too big, their problems are being caused. We're going to call this thing a class because yay us.
Okay, so just to jump in here and give a little recap, just to make sure my understanding is correct at least. So basically what happens is when you have a rudimentary set theory, so the original set theory, we were running into these problems in which we can describe things that are paradoxical, that provide these contradictions that we just can't make any sense of, like the barber. And so then mathematicians looked at this and they said, well, we really like the idea of set theory. We want to be able to use it to describe things, but we need to come up with a solution so we're not getting these nonsensical ideas. And so there are sort of three ways of approaching this. The first one was Russell's, where you very clearly define terms, and this is not an intuitive solution perhaps, but it might provide some value in its specificity. And then you have things like Zermelo's and von Neumann's, which get around the issue by introducing other ideas. So von Neumann's basically creates a class distinction, whereas Zermelo's looks and says, okay, well, we're going to restrict what we're talking about, so we can only talk about things that won't cause us to run into these paradoxes. Is that correct?
Absolutely, yeah. And I thought of a good way to tie a bow on the last distinction. ZFC is kind of like the helicopter parent, right? When we start talking about sets, we're going to assume something can go wrong, and so we're going to like put a bow on it, put a bound on it, just to make sure. This von Neumann system is kind of like the hands-off parent, where it's just like, talk about whatever you want, free, unintuitive, and then if we run into a problem, we have this magical concept called a class that will introduce at the last minute to kind of save us. Dad'll jump in to save the drowning kid, or chase him down the hill to stop the bike going crazy. That's basically how I think about it.
All right, excellent. So then are we ready to move on to introducing set theory? Or I guess I should ask, where do you want to go next?
The other interesting thing that I liked in the section, so that was the paradoxes and the rough way to solve it. The other interesting thing I saw in the chapter was virtual versus um, actual infinites. I want to touch on that because I think this is the only place in the book he does. And so we might as well, if we're going to link set theory to philosophy of religion, and this is one of the best articulated versions of the distinction I've ever found, I want to talk about this. Let me find the page. All right. So, yeah, the next thing that I thought was interesting in here was the discussion of virtual and actual infinites. So let me find where I want to start reading here. Yeah, classical mathematicians made a distinction between the actual infinite, in which infinitely many objects are conceived of as existing simultaneously, and the virtual infinite, which is simply the potential to exceed any given finite quantity. The virtual infinite was regarded as safe, hence admissible, whereas the actual infinite was taboo. So when you're hearing like William Lane Craig or another philosopher talk about, well, potential infinites might exist, but actual infinites don't. What the distinction is talking about here is the question of whether infinity exists all at once, or whether it's just a sequence of things that can always be bigger without terminating, which seems very weird. How do you terminate infinity? The way you can visualize it's like this. Imagine you have a point starting at 0, and then you make another point starting at 1, and you make another point starting at 2. And you imagine this person kind of drawing dots on a number line forever. They're always drawing one dot bigger than the other dot. So it's like, okay, well, if they keep going forever, how many dots will they draw? Well, they'll draw an infinite number of them, right? But it's also true that even though they've drawn an infinite number of dots, they can always keep drawing one dot bigger. There's no end to it. It's being counted. Whereas that's a virtual infinite, right? Where infinity is kind of like a process of generation, and you can't think about it outside of that step-by-step process. Actual infinites are simultaneous, as the book says, which is a good way to think about them. It's imagine the whole number line itself. You draw that line with the arrow in your book, and you imagine that line is completed forever. It's not being drawn dot by dot or anything like that. It's just done all at once. That is the actual infinite. And so whenever you see that brought up in philosophy, you can think back to that visualization. And I think that'll provide some clarity. So I'm kind of happy the author did that. It's cool.
All right, fantastic. So I think that covers the introduction then. We've introduced what set theory is, the problems with the original or naive set theory, and then we've touched on how it relates to philosophy and all of these interesting philosophical arguments that don't seem like they might have mathematical relevance. But when you look at it and what set theory is trying to do by break things down into logical components, then we find that, hey, this actually has a lot of relevance to these unique and distinct conversations.
Yeah, absolutely.
We'll just jump into chapter 1 here, where we introduce classes and sets.
Okay. So chapter 1, or at least this first bit of chapter 1, the big philosophical ramifications of this, big picture, actually harkens back to something he talks about a little bit in chapter 0. We don't have to go back and look at it. It's very conversational. Basically, here's the problem. The major ways the, quote, axiomatic method gets around paradoxes, especially semantic paradoxes. So in chapter 0, he talks about logical versus semantic paradoxes. I didn't want to get into semantic paradoxes too much because they're harder to articulate, and also they don't come up as much in philosophy arguments in terms of like, this is ontologically impossible, or whatever philosophers say, because we recognize that semantic oddities are kind of semantic oddities, and that's like its own separate kettle of fish, and we kind of accept that. But mathematicians care because expressibility is really important for mathematicians. In fact, let's do a slight review. When you're in algebra, I forget if it's algebra 1 or algebra 2, and they teach about functions. And when is something a function? Well, when it passes the vertical line test. If you draw the graph of the thing you're talking about, can you draw a vertical line through the graph that touches it at 2 points? And what does that tell you? That tells you that one input is mapping to 2 outputs, and that's bad because if 2 engineers implicitly assume different outputs are being given by a function, Neither of them has done anything wrong, but they get different answers, bridges fall down, not good. We like one input to go to one output. And in higher level math, that becomes an issue in terms of how terms are expressed. So sometimes you can express the same thing in multiple different ways, and if a function, because of how it's expressed, would do different things with things depending on how they're expressed, that's a problem. And this is like the semantic paradox is the most abstract version of that problem. And so that really does bother mathematicians who want things to be kind of nice and neat, not, quote, subject to interpretation. Okay, so how do we solve the semantic paradox problem as mathematicians? Well, what we do is we restrict things in terms of what's called the formal language. You'll talk about that in chapter 0. And what's that? Well, basically, you define a universe of discourse, and then what you do is you build statements in that universe of discourse to explicitly define the thing you're talking about as best as you can. So mathematicians aren't going to do very well with things like, I want to talk about the set of all people who are like Socrates. They're just going to look at you and go, okay, what does that mean? Right? You have to put it in these really crude, simple terms that they can work with, because otherwise things go off the rails. So it's another way sets are semantically restricted. So to distinguish the restrictions, this might be helpful. In chapter 0, we'd see like the curly bracket x colon thing after x describing what it is or does. To solve logical paradoxes, ZFC will restrict things before the colon. I want x's in a bounded thing that have these qualities. To restrict semantic paradoxes, you restrict things after the colon that are descriptive. And you say, I can only describe elements that follow these very basic language rules, so how things are described are very rigid. And so in section 1, what are we doing with that? So basically, so the philosophical problem with this is mathematical set theory doesn't map to all the things philosophically we want to say about sets. We have very, very big intuitions about, what sets are. But the other question is, do we? So something I literally just thought of now, this is in my notes for prepping for this video. There's a book, Necessary Existence, written by Proust and Rasmussen. And one of their first arguments from contingency is heavily determined by pluralities instead of sets. And they have to go through great pains to describe what kinds of problems can occur if you talk about like the set of all contingent concrete things. And what they want to do is they want to say, well, we don't want to talk about the set of all contingent concrete things. We want to talk about a plurality of contingent concrete things. And part of that reason is the difficulty of talking about that in terms of the math speak we usually assume for things like classes and sets and so on. So what they want to do for their arguments is have a vague philosophical gesturing, stuff that's just like those, waves hands in a general direction, right? Which we don't really have the mathematical language for, but by God, they try to analyze one as best as they can. It's this, but it's not so rigid as these things called sets. So that's the philosophical impetus behind this section, right? We're starting with these big things called sets, and we're looking at truth tables. Like, truth tables are intro to logic class. Why do we care? Well, it's because one way we deal with semantic paradoxes is we restrict things in sets or classes to what you can put inside these truth tables. And that's why. That's the big capital W why we're talking about any of this. Does that make sense?
Yeah, so I think the idea, right, is that when we're talking about these philosophical concepts, we want to keep talking about them, and we want to be able to express them in some sort of formal structure. And yet there are all these landmines that we run into when we do it in the basic underlying set theory, right? And so they have to come up with language like pluralities and this sort of thing. Is that correct?
Exactly, yeah. So mathematicians, to make sets workable, came up with lots of linguistic restrictions. Philosophers know there's a broader intuition that we all kind of have they want to exploit for their arguments. They want to just gesture and say these. And so, one of the big things to contrast in section 1, is how rigid the semantic language is to describe things inside of sets versus how philosophers would like to talk about multiple quantities of things that they'll also just often just call pluralities to get away from this. And so what should strike readers how different math sets are from philosophical sets.
All right, excellent. So then perhaps we should just start introducing some of these ideas. So here in section 2 of chapter 1, we start building these classes. So you want to talk about classes, the membership relation, all of these sorts of things?
Sure. Okay, so chapter 1 was all about the truth table stuff. If we're assuming intro to philosophy, you're probably good there. If not, you might have something for the audience on that. Assuming that's all good, and we have an idea how to describe stuff we're talking about. I want numbers that are even, but also bigger than 4, but also less than 25, right? Putting those things together using logical carve out what's in your sets in ways that you can mathematically, handle. Building classes is now a bit more abstract. Now we're going to start talking about ways of describing what is and isn't in classes more generally. So the first thing they talk about elements, right? Let X be a class. This is on page 25. Let X be a class. If X is an element of some class A, then X is called an element. So basically, one thing that the author is very clear to point out at the beginning is it's not the case that you have sets or elements or classes or elements. You can have sets inside other sets. You can have classes inside other classes. And in fact, when we move to chapter 4, he'll finally describe the foundational difference between classes and sets. Namely, spoiler alert, classes are elements of classes are sets with maybe some other implicit restrictions we'll talk about as we get closer. So this element idea, what's inside of what? What are we talking about is the layman's terms of that, right? When you're talking about elements, you're talking about what in this context are we talking about? That's an element. Now, so if we look at the next definition, let A and B classes, we define A equals B to mean that every class that has A as an element also has B as an element and vice versa. So basically, this is kind of interesting. This is not usually how we talk about, say, set equality. And this is probably something you'll learn in discrete math, number theory, whatever. Usually set equality is if every element in one set is an element of another and vice versa. But they're going meta with this. They're going bigger. They're saying two classes are equal if any bigger class you can think of containing the smaller class, or containing one smaller class, has to contain the other and vice versa. So when you're thinking about set equality, we're taught to go smaller, but in this example, he's actually going bigger. Any bigger class you can think that contains one, it has to contain the other, and vice versa. I find that kind of interesting. That's kind of cool. Now, he then gets there, he kind of restricts this down with A1. A1 is what we're used to thinking about. A equals B if and only if, if an element is one is an element of another and vice versa. So A1 is how we're used to thinking about this, but it's actually an axiom. He calls it the axiom of extent. And the definition is actually the broader thing where you go bigger. So the reader might want to look at that and play around with that a little bit and see how that makes sense to them. But then you get to the next page, Theorem 1.11, and this is where this next section is really going. Because what we're trying to do is we're trying to ultimately build classes from other classes. And he'll be doing that in future sections, but this kind of starts laying the groundwork for it. So every class is equal to itself. If one class is equal to the other, then you can always swap the equality. No big deal. you have transitive equality like you'd expect. If A equals B, B equals C, A equals C. So equality works just as you think. But there's also the subset relation that you find in definition 1.10, right? That's on the page we're still on. So subset relations you can see borrow from if-thens, right? If X is in A, then X is in B. But it's easier to think of if you draw a Venn diagram. You're thinking of a smaller circle inside of a bigger circle. So if something is in the smaller circle, and the small circle is completely in the big circle, then it has to be in the big circle. That's what that is. So that's a basic definition of a subset, and he just uses that to build, transitivity. So if A is a teeny tiny circle, and it's in a bigger circle, which is in a bigger circle, then the teeny tiny circle has to be in the biggest circle because it's circles inside of each other. Simple stuff. So most of this is just the very, very basics, like building classes. So we talked about how to describe what's in them. Now we're just talking about how to use subsets and equality to describe like nesting, putting stuff instead of stuff like Russian dolls. When are two classes the same? So on and so forth.
All right, excellent. Yeah, so I think that example of the Venn diagrams is excellent because we can imagine that for let's see, the first definition up here, 1.9, right, where it's saying that if A is an element of X, if A is an element of X, then B is also an element of X. And if B is an element of X, therefore A is an element of X. It's basically saying that, hey, we have two circles, but they're actually the same circle, right? And that's just what, A equals B is saying.
Yeah. So X you can think about is any bigger circle you could draw containing A, right? If A and B are supposed to be the same circle, then any bigger circle you can draw that would contain A should also contain B, and vice versa, because they're the same darn circle. You're right.
Yes. All right. So what we've basically done thus far is introduce the idea that, hey, we have these classes or sets, right? And we can talk about the relation between two of them, and we can do that by looking at the elements. And if if all of the elements of one are all of the elements of the others, and vice versa, we actually are talking about the same set.
Yeah.
All right. So then, should we move on to a little bit of the language here?
Yeah. So the theorem I just talked about, that's basically all the transitive laws of equality, the transitive laws of subsets, right? A is a little circle, B is a bigger circle containing A, C is a bigger circle containing both of them. Nice and easy. He does some proofs, and the proofs are kind of interesting because these things are kind of obvious. But if you and the readers are going to do exercises, just looking at how you prove things. So here's something I learned when I took math classes. Oftentimes you learn more about how to prove things that seem obvious to you using the language you're supposed to be using than you do how to prove complicated things. Because complicated things, you can kind of look up a solution online or see your teacher do stuff, and you can kind of like go with the flow and just kind of plug stuff where it's supposed to go, and things work. But when you're forced to prove things where it's like, well, of course this is true, duh. Well, the point of the exercise isn't to literally prove it's true. You know it. The point of the exercise is to translate basic things into a language to get the results in the language you expect to get. And once you do that, then the more complicated proofs will make sense to you. There's a reason why you're plugging the things where they're supposed to go. There's a reason why the solutions are written out a certain way. So if you look at those, then it's pretty nice. So like the proof of the first one, A equals A. Well, they're using axiom A1 here. So the definition they gave involving, putting circles inside of bigger circles to show it's the same circle, that's too cumbersome for most mathematicians. So A1, the subset definition, two sets are equal if they have the same elements, basically. That's the applicable ones. That's what they're using, right? So look what they say, right? The statement X is an element of A implies X is an element of A. And you would switch them, right? You should have X is an A implies X is an B and vice versa. But because it's the same set, there's nothing to do there. You only need one. You just need, if x is in itself, then it's obviously in itself. It's obviously true. Why is it obviously true? Well, anything in itself is an element of itself. That's why. So all these are going to be kind of obvious in the same way, but the important thing is to look at how the language is broken down. Because if you're trying to like follow how this is proved and constructed, that's where the exercise is. Is there anything else that's interesting here in this one? Yeah, I want to look at A2 for a second while we're here, because this is where the language starts really getting messy for people, and I think we should talk about this. I mean, listen to this. Let P of X designate a statement about X which can be expressed entirely in terms of symbols, blah, 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 blah. Then there exists a class C which consists of all the elements that satisfy P of X. Okay, let me explain like what this is intuitively saying, and then I'll try to break down this jargon. What this is saying is, let me use like numbers for an example. We all know we're talking about numbers, and we're talking about some numbers and not others. So I want to talk about like every other prime between 20 and 100. So P of X is kind of like my restriction. It's my predicate. I'm not just talking about any numbers. I'm talking about every other prime between 20 and 100. That's like the P of X. It's the specificity. It's the what we're talking about here. Now, can be expressed entirely in terms of symbols. I will admit that this kind of stuff I'm a little baffled by, because this is too strong. It's not expressed entirely in terms of those symbols, because like let's suppose we try to like collapse this every other prime between 20 and 100. What I want is numbers that are prime numbers and greater than equal to 20 and less than or equal to 100. That's kind of what they mean in terms of expressed in terms of symbols. It's not entirely, because we haven't broken this thing called a prime number down in terms of ands, ors, nots, and so on. We still have primitive notions, and we will have primitive notions. You look at set theory as like an intro topic to so many things: group theory, topology, category theory, you name it. And every one of those mathematical disciplines are going to have primitives that you kind of can break down, but eventually you kind of reach a point where there are primitives. We're not machines that communicate with machine language. You get to a point where it's like, okay, here's a broad concept. We kind of know it when we see it. We're going to move on. He even mentions this in chapter 0 with like planes and lines. We know what planes and lines are, but at a certain level of like, Euclidean geometry, you don't rigorously define what those are. You take them for granted and move on. And math has a lot of things that are just like that. So it's not that they're expressed entirely in terms of symbols. It's more that they're symbols, brackets, and variables. So the variables are kind of like the primitives. They're kind of like the elements. They're kind of like the things that go in. In general, little things are elements, and big things are classes. Is basically how I want to distinguish, big letters from small letters. So this is called the axiom of class construction. So what it's basically saying here is, if you can take these symbols, take these primitives, and take these variables these primitives are arranging over, like x is a number, you have this primitive called like a prime number. And you kind of you put primitives, variables, symbols together, and you build them up with Legos, let's say, like linguistic Legos, truth tables, all this stuff. If we've gone through all this work, have we created a class or not? And what this axiom is saying is, yes. If you're faithful and you follow all the rules and you use primitives within your universe of discussion, you use these symbols, you use the correct variables as elements and sets and so on in the curly brackets, at the end of it, you will have constructed a class. That's all this is saying. That's all this is saying, like intuitively speaking. But it looks like a lot because they're throwing a lot at you. P of X, the symbols, all this. But if you get used to the nomenclature, P of X is just something we're saying about something. It's a predicate, P is for predicate, basically. Symbols, elements, and or blah, blah, blah. This is like the mathematical jargon we use to make the statements along with our primitives. And these little variables here is just saying what's inside of what. And if you do all this, then you're eventually going to get, a class at the end of it. You're not going to waste your time, is all the axiom saying. But the language looks confusing, but what it's conveying is actually really simple. That make sense?
Yeah, so just to jump in here, so when we're talking about let P of X designate a statement, it's just imagine that we have some statement which it's going to have these symbols, it's going to have variables, and potentially we'll have brackets, right? And this will define a class that we're talking about, right? In this case, there's the class C, which will consist of all of the elements which satisfy P of X, which basically means that, hey, this rule is saying that there's going to be this class out there, and if you follow all the rules, this class C has all of the elements that are within the statement P of X.
Yeah.
Yep.
That's it.
Excellent. So do we want to move on to axiom or I guess that is axiom A2. So we can just move on then. Let's see.
Yeah, so what we just talked about was basically the axiom A2.
Right. And then if we go down to the bottom of page, is it 27 here? I only, each page is broken down to me into 26, so I don't have odd numbers.
Oh yeah, it looks like 26. Yeah.
Okay. Yeah. So then we have C is equal to, and then we have basically axiom A2 restated. And so if you want to just read this out in non-math terms, how does this read?
Yeah, so how this reads in non-math terms is C is the class we've constructed at the end of all this. So remember what we said in A2. A2 at the very beginning was let P of X designate a statement about variables and blah, 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 blah. What that's saying is here's how you put it together. The class we construct by the axiom, we're guaranteed this class, C, that's equal to all the little x's, colon means such that, P of X. They satisfy whatever the statement is you built from them, using your primitives, your ands, ors, and so on, and all that. And that's it. So the crux of all this is just remember the anatomy. Everything that becomes before a colon is just describing broadly what we're talking about. We're talking about people. We're talking about numbers. We're talking about whatever. And then the P of X at the end of it is specificity. So if I say people like Socrates, I might be saying I want all the little x's to be people such that, and then the P of X would be something like they're like Socrates. And this is the part where the mathematician's going to look at you with angry eyes and say, I can't deconstruct like Socrates into things involving ands and ors and nots and so on. You'll have to be specific. In what way are they like Socrates? Do you want to restrict their height so they're between this tall and this tall? Do you want to talk about how many people they make mad, angry at the marketplace today? Right? They're angry like Socrates in that there's a probability they will make between this many and this people angry at the market today. Right? Give me some specifics I can use with base primitives we have to take for granted in symbols. Don't give me vagaries like Socrates. And if you do all that, you kind of have your class.
Right. Yeah. So and these, it isn't like C is specifically designated. We could imagine any of these being, so we could say B is equal to, and then let's imagine going off your Socrates example, let's imagine that it's philosophers, right? So we'd imagine that we have a rule which is if anyone is a philosopher, then they're in the class that we're talking about. And so X could be, any philosopher, right? So we'd have Russell in there, could be an X. We could have Wittgenstein, right? We could have all of these guys.
Right. And then the such that, the colon would distinguish like what about them we want to talk about. So any philosopher such that they lived past the age of 30 or something like that. That's something we can use to quickly, nip this in the bud.
All right, excellent. So then moving on here, we're going to start adding more definitions.
Yes. So where do we want to start? Do we want to start with 1.12 here? Let's see. The use of small x in the expression is not accidental. It's quite essential. Yeah, because you want your little x's to denote elements, and you don't want to accidentally determine like classes in terms of themselves and things like that. Yeah, the letters little x, little y, etc. will be used only to designate elements, and you want to predicate on elements. That's a really big deal. Let's see.
So remind us what makes the difference between an element, a class, and a set.
Okay, so class and a set, unfortunately, he's not going to touch on until I think it's 1.4. But again, to spoil it for everybody, things that are elements of classes are sets. I think there might have been some other little restrictions closer to. I haven't, looked over all the details to make sure because I didn't think we would get that far today. We're probably not going to. So don't hold me to that completely. But the big gist of sets versus classes is that so here's the trick. Here's the interesting trick being played. You remember how I said earlier that ZFC solves Russell's paradox and the like by restriction, by saying we're going to make sure everything before a colon is, let little x be elements of some universe of discourse that kind of ropes them in to make sure things don't go crazy. Kind of like the barber not living in town when the barber paradox comes up. That's the way. And then I said, well, that's kind of unintuitive because we don't like to properly distinguish when we talk about that. Most of the time we'd like to be, people. Are they people on Earth? Are they people on Greece? Are they people in Europe? Who knows? People who, blah, blah, blah. We like to be a little bit more unrestricted. And so the idea of this von Neumann idea is to preserve that intuitiveness of freely talking about stuff. Note that C is just X such that P of X. It's not X in some universe of discourse such that. So it's like, look here, we got this class of just free-ranging stuff. Isn't that cool? But the trick is that sets are elements of some class. And so you kind of backdoor the whole universe of discourse thing anyway. It's just that you're saying your universe of discourse is the at least one class to which your set of stuff that you're talking about belongs. So they end up kind of getting to a similar place in the end. At least it seems to me from looking at it. But I'm pretty sure there's going to be some like foundations of math guy who's like, read all Principia Mathematica. He'll be like, well, actually, here's this 20-page proof about where all the differences are. It's like, wow, that'd be interesting. I have no idea, but it looks very, very similar to me that you're just defining your universe of discourse as the class that your sets kind of live in. So that's the difference between a set and a class. Class is like the really big thing that binds sets. And sets are things in classes that may or may not have other rules. Now, sorry, you wanted me to redefine sets, classes, and elements. That was the third one. Elements. Yeah, an element is just something inside something else. That's it. So you can have classes inside of classes. The class that's inside the other class is called an element. You can have sets inside of sets, like power sets. We'll talk about them later. So a set inside of a power set is an element of that power set. Anything that's inside the other thing, like a Russian doll, right? Any little doll inside a bigger doll is an element of that bigger doll. That's all you have to think about for that.
All right, excellent. I think that this is probably a good point to leave off here. I feel like we did a good job on covering the basics, and then we can start introducing concepts like union, intersection, the empty class, all of these things in the next episode. So
I agree.
Yeah, if you could just give us maybe a couple sentence recap of what we've talked about here, just to wrap everything up with a bow.
Yeah. Okay. Few sentences to sum up all this. Sets are useful for philosophy, either explicitly for like Kalam arguments, or implicitly for things like what does it mean to know all truths, or even implicitly in terms of some arguments that need to talk about stuff but are afraid of fallacies of composition. So pluralities in Proust and Rasmussen's argument, they come up everywhere. We want to know about them. We thought we knew about them. We screwed up. There are paradoxes. We tried lots of ways of fixing them. The ways we tried to fix them were defining things in universe of discourse explicitly, ZFC, implicitly with this idea of classes, that's the von Neumann stuff this book is going to use, or being very, very rigid about what's inside of what, which was like Russell's type theory. The other way you could solve it is you could be an intuitionist. He talks about that in section 0, or chapter 0, which is a whole nother can of worms. So we talked about that. We made a little note about virtual versus actual infinites. That note aside, we started, digging in here. The first thing we said was we have to start building sets using kind of a rigid logical language to avoid semantic paradoxes, which he talks about in chapter 0, and I encourage the readers to kind of look into, but it's really hard to articulate that even with notes. That rigid logical language doesn't make philosophers happy who have an idea of stuff but can endlessly argue about how to reduce it down definitionally. Some of those debates will never be resolved. So that's a really big impasse between math and philosophy as far as like what you do with the need to rigidly describe stuff to avoid some problems versus the need to freely express our intuitions to make broader arguments. Once we talked about the language of logic, ands, ors, equals, whatever, vague gestures at truth tables in the first section you'll probably talk about later. We talked about the point of all that. We want to take it for granted. It's there. You can do some exercises about it. Next step is to just make obvious statements. Certain classes are equal to themselves. They're equal to each other if they have the same elements. If one's a subset of another, is a subset of another. Transitivity. Russian dolls. Small Russian doll is in a bigger Russian doll is in a bigger Russian doll. The small one is still in the biggest one. Very obvious statements. We briefly looked at the ways these arguments are made by chasing elements around. So the point isn't that they're hard. The point is get used to expressing obvious things in this language if you want to follow the proofs. We talked about a hard to describe axiom. The axiom of, I think it was called constructibility, where you have this weird thing called P of X. What's that? It's a predicate describing what you're talking about, not just numbers, but these kinds of numbers, things like that. And we described how you can take these primitives like number or prime number or whatever, point, line, logical symbols and elements to build this class C. It's the x's such that this thing's true of all the x's. Cool. That axiom just says you'll get to things at the end of it. And that's basically it. We ended with just kind of like the anatomy of what all this stuff is. Curly brackets to define things in your class or set. The stuff before the colon is what you're talking about. People, chairs, philosophers, trees. The P of X is what kind? Tall trees, short trees. How big are short or tall? Nothing qualitative. It should be logical and quantitative enough to use symbols and things like that. And that's about it. So hopefully that kind of wraps it up for people, and there's the big picture.
All right, so that concludes episode 1 on our series on Charles C. Pinter's book, A Book of Set Theory. I know that this episode was a bit longer. We aim to have the future episodes be a bit shorter, but given it was the first episode, there was a lot to introduce. It was going to be a longer one, but probably aim for about 30 minutes. Of course, that'll be content dependent, depending on how complicated the ideas are to introduce. In between episode 1 and 2, I'm going to try and drop an episode that just reviews logical truth tables and or for anyone who's not familiar, introduce those ideas because they're so important to what we're doing in set theory. It's not going to be a super in-depth video going into those it'll just be an overview, but hopefully even if you're not familiar, it'll sort of give you an idea of what we're doing here because logic is the foundation of set theory. I'm hoping to get episode 2 up in about a week or two. I'm hoping to edit each of the videos either in a week or 2 weeks, but depending on how long they are, they take multiple times longer to edit as they do to record, especially as I'm still teaching myself how to use the editing software. So expect it in a few weeks here. And if it isn't out by then, feel free to drop a comment in the comments, and I'll give you a updated time that I think it'll be edited by. If you guys have any questions, also please leave them in the comments. I will either make standalone episodes every few episodes, or maybe at the end of each of the episodes, I'll ask Logos to go through the questions and answer them, or we can post answers in the comments. Comments might be a little bit hard just because we can't type notation. So as we get further and further into the book and things get harder to explain, that might not be a possibility, but we'll be sure to address any of the comments in the videos themselves. So with that, I hope that everyone enjoyed, and see you in the next episode.